Welcome back, class. In today's video, we're going to be diving a little bit deeper into this concept of the energetics of mixing. So, in the last video, we talked about the balance between the energy that it takes to break the solute-solute interactions and solvent-solvent interactions, and balancing that with how much energy is released when you make the new solute-solvent interactions. So if we think about that a little bit more quantitatively and sort of look at each of those scenarios or each of those ideas, we can come up with an equation. So the first thing to remember is that to break interactions, right, always takes energy. So if I'm mixing, one of the things that I have to do is to break the solute from each other and the solvent from each other. So I have to break those solute-solute and solvent-solvent interactions. Both of those are going to be endothermic processes, right? They're going to take energy. Now, if I want the solution to form, right, I have to get back or recover that energy in order to make that solution favorable. So we looked at those different scenarios, right? And so forming the new attraction between the solute and the solvent is exothermic. We call that the delta H of mixing, or the enthalpy of mixing. So we have these three terms. We have two terms that are endothermic. Now remember, sign-wise, right, enthalpy, right, if we add energy, that's a positive change in enthalpy, right? So it's going to be positive component. And then we have delta H of mixing, which is going to be a negative sign. So we have these two parts, right? We have these two positive terms and we have the negative term, and we're going to add these together, and the outcome is this is either going to be positive, right, or negative, right? If it's positive, then the solution may not form depending on the entropy, right? If it's negative, then the solution will form. And so these are the ideas that we're going to be just looking at a little bit more in detail here. Okay, so let's look at some pictures. So let's look at scenario number 1. And in this case, we can see by looking at breaking up our delta H of solutes and our delta H of solvent. So 1 and 2 takes a certain amount of energy, right? Now in this case, the delta H of mixing, the amount of energy we're giving off, right, is greater, right? We get more energy back. So of course the difference, right, when you add 1 plus 2 plus 3, right? In this case, we're going to get a negative answer, right? And that negative answer is going to be equal to whatever this will be, right? We have an exothermic process. Energy is overall given off. And so our delta H of solution is negative. The solution will form. Pretty straightforward. How about example number 2? Here, right? Well, here it takes more energy, right? We have to put in more energy to break our solute and to break our solvent, and we don't recover enough energy from our mixing, from making our new solute-solvent interactions. So we end up with a deficit, right? In other words, it costs more energy than what we recover, and so we get an overall endothermic process, a positive change in enthalpy. So it's in the system, right? There's an overall increase in the energy of the system, right? And again, it's not as simple as just saying the solution won't form. We have to say the solution may form, and this is where we have to address the entropy component. Is the entropy increase the spontaneous mixing part of this whole picture, enough to overcome this difference. And it really depends on the size of that difference. Now, there is no number I can point to. Every situation is going to be a little bit different. Now, at this point in time, we are not looking at this kind of scenario, predicting whether this will form, because we're not going to quantify the entropy right now. So it's just, you could make an assessment that in example 1, it will form. Example 2, it may not form, right? You could calculate the number and you could come up with one of those two outcomes. Now at this point, I want to address a special scenario. So again, there's a lot of special scenarios that surround water, right? Because we are dealing with almost exclusively aqueous solutions. So the special situation we're going to look at here is dissolving ionic compounds in water. And so it's the same basic idea, right? There's still these three parts. We just have a special way of looking at it. So there's a special term called the heat of hydration. So the heat of hydration is something that we think about when we mix an ionic material with water, right? And it has to do with developing these very strong ion dipole solutions. Now, the way we get to that is we take the amount of energy it takes to break the water, the solvent, from each other, so to break those hydrogen bonds. So of course, right, that's going to be a positive value. And we combine that with the delta H of mixing, how much energy is given off when you form these new ion dipole interactions. Now remember, right, the solvent in this case are going to be those very strong intermolecular forces, ion dipoles, and we have hydrogen bonds, right? So to break these is some positive number. You're going to form these, it's some negative number. And you add those two terms together, this is where we get the heat of hydration. So the bottom line is, when working at these aqueous systems with ionic compounds, we just solve it a little differently, because the term that we're often going to have available to us, right, the term that we're going to be able to, they're going to give us or we're going to look up, is going to be what's called the enthalpy of hydration. Now, this is almost always negative, and pretty much in all the examples that we give, the delta hydration, the delta H of hydration will be a negative value. And the reason for that is that you release a lot of energy when you form these ion dipole interactions. And remember, you make a bunch of them. And so when you combine the energy that it takes to break the hydrogen bonds, and you combine that with the energy you recover from making these new ion dipole forces, this is almost always bigger. And sometimes much, much bigger. And so the heat of hydration is almost always negative. Now, so it really becomes now our negative term, right, in our system. Instead of the mixing, now we've created this new term, and we're really comparing it with the delta H of solute, right, which of course is going to be positive to get our delta H of solution. So it's just a little different formula. So now the heat of solution, instead of having three components, for this particular situation just has two components, right? The delta H of solute plus the delta H of hydration, one positive, one negative. The bigger one's going to win. Now, when we deal with these particular kind of solutions, another thing to think about is the delta H of solute is going to come from something that we've talked about before, and that is the lattice energy. So remember, the lattice energy is the energy that is given off when a crystal lattice forms. So when you bring all those positive ions and negative ions together and you form all those ionic bonds to form that crystal lattice, a bunch of energy is given off, right, when you make those new bonds. That's the lattice energy. So remember, lattice energy is typically a very large negative term, right? Now, the delta H of solute is simply the opposite of the lattice energy, right? It's going to be a very large positive term because you're breaking apart that ionic crystal. So you're breaking those ionic bonds, so you're going to have to input that amount of energy equivalent to the lattice energy to break everything apart. And so the delta H of solute for an ionic compound is simply the opposite of the lattice energy. So in this particular situation, of course, this is going to be positive, right? Because our lattice energy is always negative. Okay. Let's look at an example. So, we have our basic equation, solute plus hydration. So if we look at, in this case, dissolving Kf. So, when we dissolve it, the energy to break up our solute, right? So the lattice energy for Kf, right, is negative 821 kilojoules per mole. So that means the delta H of solute is 821 positive kilojoules per mole. So it's going to take 821 kilojoules per mole to break the potassium ions from the fluoride ions, right, to generate the free ions. Now, how much energy do we recover? Well, turns out the heat of hydration for Kf is negative 119. So if you simply add these terms together, positive 821 plus negative 819, you get a positive 2 kilojoules per mole. Now, what of course does that indicate? Well, it indicates that this solution, strictly energetically speaking, is not favored, right? Because it takes more energy, the positive term, it takes more energy to break the crystal apart than we recover when we dissolve it in water, right? The heat of hydration. But it's a small amount, 2 kilojoules per mole. And so this is one of those examples where that entropy is going to come into play. Now, from practical experience, right, we know that potassium fluoride dissolves. And it dissolves because of that entropy change, right? Because of that drive towards spontaneous mixing, right, is enough to overcome the relatively small endothermic of this particular solution. So in practical experience, right, when some compounds, such as ionic compounds like sodium hydroxide, dissolve in water, you get a lot of heat released, right? They're very exothermic. You might even sense heat getting on the dictator, right? It gets physically hot, right? You could do this in calorimetry, right? Now, other ionic compounds, right, are less soluble, right? It's not a one or the other, right? There's variable solubilities. Some can you dissolve a lot, some you dissolve very little. And that's because some of them, like we saw with Kf, but even some to a greater degree, like ammonium nitrate, are actually endothermic, right? So have something similar to what we just saw, that you don't recover enough energy, but it still dissolves because of the entropy. And oftentimes we might feel those containers get cold, right? Now, you might remember from Chem 1, I gave this example way early. We talked about exothermic and endothermic. That ammonium nitrate is one of the compounds sometimes used in chemical cold packs, that when you dissolve that ammonium nitrate in a aqueous sort of gelatinous material, right, it's endothermic, so it pulls the heat out of that gel, causing the gel to get cold, and that's where you get the cold pack idea. But it still occurs, again, because of that second factor, that entropy factor. All right, so that wraps up the ideas here with energetics of mixing. In the next video, I'm going to look at how solubility varies with temperature and pressure when we think about gases.